definition. I'm not used to addressing physics audiences and see some strange effects of gravity because the audience will be shifting to my left. So I'm very grateful to Tom and Eugenia for having laid some of the background material and foundations on higher categories. I will propose in Tom's terminology, I would like to do two things. I would like to propose a 13th definition of higher category. Or did you didn't include me in 12, did you? And
you're number one.
I will also show that the narrow view on higher categories, the Lurie view, includes some others. So, I will write cat for the small category of categories. It's a small category of categories, and cat E for the category of E-enriched categories. And as you all know, this makes sense for any symmetric monoidal category E. And as we proceed into the talk, I think the prime examples to keep in mind are the case where E is topological spaces with a Cartesian product. So, for example, cat top is topological categories. So if you pronounce the phrase topological categories, it's a little bit ambiguous. So the way I use it here, I mean a topological category whose space of objects has a discrete topology. That's the same thing as a category enriched in topological spaces. And the other example is categories enriched in categories. That's a category of two categories. Okay? And more generally, one can define, let me try to be consistent in the notation, cat n plus 1 is cat n. And so this is strict higher categories. But to get started, of course you have to say that cat 1 is cat, or even, I can only go down to 0, so cat 0 is set. So one of the things I would like to do, is that readable all right? Too much reflection? Bad handwriting?
No, just reflect. It is a bit difficult to read.
Sorry?
It is a little difficult to read. Maybe reflection.
I will move to the middle board. So one of the things I would like to do is to give a similar definition, inductive definition of weak n categories. Well, I will not define individual weak n categories. I will define the entity of weak n categories. So one of the goals give a similar definition weak cat n plus 1 is cat of weak cat n. And I have to start somewhere, and I could talk for a long time about whether to start at 0 or 1 or 2 and how various ways of looking at this. But maybe the easiest for now is to say that weak cat 2 is my categories. Now, one of the things in this approach that is quite different from the one on the board that's difficult to read is that this thing here is something a little more general than a symmetric monoidal category. I'm also going to use red and blue. It's no longer a symmetric monoidal category, but an infinity-operad. Now those are the infinity-operads from the title. And this is a weakening of the notion of symmetric monoidal category in the sense that the symmetric monoidal category is faithfully embedded in infinity-operads, as I call it. Besides. So one of the things I would like to do is to explain to you what an infinity-operad is. So, what is an infinity-operad? And before I do that, I would like to step back a little bit and explain to you what an infinity category is. And to avoid any ambiguity, I think I should use the name Lurie in this sentence. So what is a Lurie-style infinity category? So, an infinity category in this sense is a special kind of simplicial set. So, the picture that you should have in mind is that here is the category of categories, which is, as I explained, and it sits inside the category of simplicial sets by the nerve function. And another category that embeds very nicely in the category of simplicial sets is the category of topological spaces by the singular function. So, a simplicial set is a little like a generalized category, and it's also a little like a generalized space. And in fact, among topologists, well, among a certain school of topologists, space is just another word for simplicial set, because for many combinatorial and categorical and homotopical arguments, it's much easier to work with simplicial sets. So I remind you that simplicial sets is a pre-sheaf category where delta has its objects the natural numbers, but I write them with round brackets, and I think of them as the linear order up to n. So there's an object for each n bigger than or equal to 0, and the arrows are monotone maps. Not strictly monotone necessarily. And you can view delta also as a subcategory of spaces. Also for every n, we have the standard topological n simplex, delta n, Rn plus 1, so here's a picture of delta 2. And this is a covariant functor from delta into topological spaces. If you have an increasing map, you can view that as a map on the vertices and extend it as a defined map on simplicials. So delta has the objects of delta have a rather hybrid nature, you could say. They're partial orders, or linear orders in fact, so you could view them as categories, but you can also view them as spaces. And that accounts for these two functors. So the minimum of C at n, which is usually written, by the way, as nerve C sub n, is functors from n to C. So for n bigger than 0 at least, that's the set of all strings of this kind. Maybe it's, well maybe I prefer not to do it like this. I might get confused. And S of x at n is maps delta n to x for topological space. So those are these two embeddings. And both embeddings give rise to simplicial sets of a rather with special properties. And these properties are related to the notion of Ken complex and variations of that. So the simplicial set is called Ken complex for an infinity groupoid in the sense of Lurie. If it does the following property. Whenever you have a map from a subobject of the representable object, so of a specific kind, then you can extend it to this map. So this is the representable. This is delta blank n, representable. And if you think of this delta n geometrically, you can build a subobject which consists of all the faces except the one opposite k. So union of all faces except the one opposite kth vertex. So for n equals 2, the picture is this. Delta 2 looks like a triangle. Let's say 0, 1, 2, and this would be 0, 1, 2. This would be lambda 1. And this would be lambda 0, for example. So it's a very fundamental notion of a simplicial set. It was already defined by Kant himself in the late 50s. Because these are exactly the simplicial sets that look very much like spaces. And every S of x has this property. So every S of x Now, it's not true that the nerve of a category is a CAN complex. The nerve of a category is a CAN complex. So however, N of C is a CAN complex if and only if C is a groupoid. That sounds rather negative. N of C is rarely a CAN complex, but the nerve of a category always has a property which is a little like that of a CAN complex. It has the same extension property if you don't allow the extremities k equals 0 and k equals n. So, the good news is N of C does have this extension property. Name star if 0 less than k less than n. And this extension property really codes up the composition in the category. Nothing more than that. This encodes composition. And in fact it does have, because composition is uniquely defined, it has the unique extension property for 0 less than k less than n. So, a definition, a simplicial set is an infinity category if, let's give it a name, simplicial set X is an infinity category if it has the extension property star for 0 less than n. And intuitively this means that compositions exist, but they're not unique. How? They're unique up to homotopy. And these homotopies can be viewed as invertible 2 cells. They are however not unique, so they're invertible only up to a 3 cell, and so on and so forth. So, just to repeat what Tom said, this can be viewed as a particular model, for a notion of higher category, weak higher category, all of whose n cells for n bigger than 1 are invertible. Let me put invertible in inverted commas because it should really mean equivalence in some sense. Invertible, an n cell is invertible up to an n plus 1 cell, which is invertible as well. This line. Move it up maybe. Now, the theory of these infinity categories is at present being developed. The definition already goes back to Boardman and Vogt in their famous Springer-Leckie notes about homotopy invariant algebraic structures. But it is only in the last decade or so has been developed by Joyal and by Lurie. And one of the things I show is that there is what's called a Quillen model structure, a notion of doing, a way of doing homotopy theory with simplicial sets, which is much more like working with categories than with working with spaces. And for the experts among you, these infinity categories are exactly the fibrant objects in this model category. So, we write that down. They are the fibrant objects. Sets. Now called the Joyal model structure. And this, when I say that it makes simplicial sets look more like spaces, more like categories than like spaces, I can make this precise because there's also a theorem which says that this model structure is equivalent to one on topological categories. So you get two views on two different views on the same homotopy theory. One working with simplicial sets and infinity categories, and one with categories enriched in topological spaces. So you can read all this in Lurie's book. But this particular equivalence is due to Lurie, but there's also some input by Julie Berger. Right down in there. So, I promised to try and give you an explanation of what an infinity-operad is. So, I want to extend this picture in the following way. Categories sit inside operads, and I would like to be able to take the nerve of an operad, and here I get a new category which I call dendroidal sets. And that's an extension of simplicial sets. And so I'm going to give you the precise definition, but since I don't know how far I will get, let me say now that these dendroidal sets I developed jointly with my student, former student Ittay Weiss. And at present I'm developing equivalences like this. For example, these dendroidal sets will be equivalent to topological operads together with also with Clemens Berger from Nice and Denis-Charles Cisinski from Paris. So I will try to tell you a little bit about what we are doing. But first, these dendroidal sets. And I have no idea how to complete the picture this way. So, if you're an expert and hence you're bored, you might try to think a little bit about what to put here. probably all seen operads. We spoke about infinity-operads, infinity-operads. So an operad P is given by a set or a space, or maybe a category of operations P of n reach and bigger than or equal to 0, and then a way of composing these and operations. Well, I used that word already. And given composition. So you should think of this P of n as operations. So think of elements P in P of n as operations P of x1 as n of n variables, and then you can plug in n new operations in a given one. And you can also commute the variables. Yeah? So you get P of n plus P of k1 plus P of k and P of k, where k is k1 plus km. A substitution substitution for composition, and one can also commute the variables in permutation of variables. So that's sigma and sigma n. N, and it sends P of x1, xn to P of x sigma 1, sigma n. So that's the structure of an operad. So typically, I will give an example in a minute. I would like to go here. It's also possible to not have just operations with n specified inputs, but let these inputs have a specific type or a color. Yeah? You get to the notion of what in some circles is called the colored operad, in some other circles is symmetric multi-category. So a colored operad is given by set C colors, and for each sequence C1, Cn, C of elements of colors, a set of operations, a set or space or category, a chain complex, and so on. P of C1, Cn, C, and to be thought of again as operations P x1, xn, but now the variable xi should have type ci, and the output, the result, P of x1, xn should have type C. Okay? And the substitution should respect these types. So you should only substitute operations whose output has the type of the input of P. Okay. So now, these operads and colored operads, they are meant to encode algebraic structures. And there are two prime examples, namely you could take P of n equals sigma n, that's the ordinary operad, and then a P algebra, which by definition, i.e. a set A with actions Pn plus A plus A n times. So that's an operation of n variables picking up n inputs from the set A and producing an output from A. Is exactly, will be just an associative algebra. So you take a permutation, you permute the order of the inputs, and then you multiply them together. And if you think about it, that's the only thing you can do. So if you look in any book about operads, that will be the first example. Now there is a very similar example. So this operad is also could be associative operad. It is usually written A or S. So this B is S, A, associative. There is a very similar example whose algebras are categories. But now you need to go to into the realm of colored operads. So, example 2. For any set S, there is a colored operad which are called A sub S, with a set of colors pairs whose algebras are categories with S a set of objects. So let's go to this board for a minute. So an algebra for an ordinary operad is just a set on which the elements of the operad act as operations. Now, an algebra for a colored operad should have a set for each color. Yeah? So an algebra for P has a set. So let's call it A then. As a set A sub C for every C and C, and actions. Now P of C1 C, so this is elements here are supposed to be operations who take n inputs, one of type C1 up to one of type Cn, and spit out the output type C. So if I plug in these inputs, I should get an output. So you can write down an operad whose algebras now have the color S cross S, and an algebra, so A of C1, let me call it ST. So the color is now a pair, and this is supposed to be the set of arrows STP for an algebra A. So that's the intuition. And I think with this intuition you can figure out yourself an explicit description of this colored algebra. Okay. Now, any category can be viewed as a colored operad. Because any category is a colored operad whose colors are the objects of the category and whose operations only exist for n equals 1. This statement is similar to the statement that an operad, uncolored, which only has operations for n equals 1, is the same as an associative algebra. Now, you only have operations px1 for one variable, and you can substitute them one into the other. That gives you the multiplication of the monoid. So that's the symbolic. So now I want to explain to you what this category is, and try hopefully have time to tell you a bit about its properties. And then you will see that one can take the nerve of the operad in exactly the same way as one can take the nerve of the category. So, this. So, dendroidal sets category these are dendroidal sets. So, the category of dendroidal sets is again appreciative category, just as the category of simplicial sets. So, simplicial sets is it still on the board? No. It was sets to the delta op. This will be sets to the omega op. So, these sets equals sets to the omega op. And now the objects of omega will not be linear orders, but will be trees. Now, if a mathematician uses the word tree, all his colleagues will say, what do you mean? There are too many notions of tree. So, I mean, let me first draw a picture. My trees have edges and vertices, just like any tree, but they have a root, well, they're finite. They have a root, and they have input edges, also called legs or leaves. So these are input edges. Inputs. So here, this tree has, I usually draw the root at the bottom, so this one has 1, 2, 3, 4, 5, 6 inputs. And each vertex has a number of inputs and one output. And this number of inputs at a particular vertex can be 0. Then the tree stops here, right? The trees are not necessarily planar. Of course, as soon as I draw a tree, it will be planar, or I give it a planar structure rather. Okay? But this is a tree. now the arrows, delta, this category of linear orders, will be a subcategory of omega. And so there will be a function like this, and on objects, it will do the following. It will send n to this tree. So edges 0 up to n operations and n plus 1 edges, n vertices and n plus 1 edges. I say this now because for those of you familiar with simplicial sets, the arrows in this category omega will also carry names like the ones in delta. There will be faces and degeneracies. So arrows in omega. Well, first, I will not say too much about this, but there are isomorphisms of trees. So, for example, you could commute these three edges. There will be edge contractions. So, let me draw the same picture again, maybe, if you take notes, you have some space left. I hope this is the same thing. So let's take an edge here. So you can, there is an arrow and it goes in this direction, that's important, which contracts this edge. So that will result in the following tree. These three edges come here. Here's the third one. And I call that delta E. And I call that an inner face. Maybe it should be called co-face. Inner face. Sorry. And there is a third type of arrow, namely chop off a top vertex. So if I number these types, 1, 2, so this is an arrow of type 2. I will now draw a picture of an arrow of type 3. I can, for example, chop off this part of the tree. Let's chop it off more than a vertex. I will chop off this part of the tree. Just write some generators for the arrows. In this tree, so if this vertex is V, I think we call this delta V. There's an arrow of type 3, and it's called an external face. Okay. And you can also chop off the root. I'll draw this diagram again. So there will also be delta of W, which is also an arrow of type 3. This is delta. Did I do it correctly? W, this is not W. W was here. Did I do that correctly? And finally, the final type of arrow is the one where you insert unary vertices. These are like the degeneracies in delta. Full insertion of unary vertices. So let me draw an arrow of type 4 here. I cannot. Well, I can, but I have to go the other way. So this is an arrow of type 4. So let's take this edge, for example, let's call it A. And I will insert a vertex on the edge A. I will cut the edge A in half. Okay, so this is A1, A2. I'm sorry. So this arrow, so you insert the unary vertex, but the arrow goes the other way. You might call this sigma A. I will call this that is degeneracy. Now, if you work this up on the image of delta, you will find exactly the usual errors of the usual errors generated in the category delta. So the arrows, all arrows in omega are compositions of these.
It's not a partial order.
Sorry?
So a tree is like a partial order.
Yes.
And are these just the order preserving maps?
Well, there are various ways of looking at it. Well, you have to be a bit careful because you either lose vertices or edges. So. Yes, I think if you would as a partial order on the edges, then that's all right. Well, you have to more precisely. You have to view it as a multi-partial order. It's for example, is this a map of partial orders? This is not a map in my category. No. So one way of thinking about these arrows, well, there are 10 ways of giving equivalent definitions, but I have to keep an eye on the clock as well. So let me, I'll do that. So now there is a nerve functor from operads to a dendroidal set, and what you do, if you have an operad P, you want to calculate its nerve, and it's supposed to be a presheaf of this category omega. So, for every tree T, I should specify a set. Yeah? And this is all labelings of T consistent with the structure. Well, let me write it. All labelings of edges of T, like colors of P, and vertices of T by operations of T consistent with the structure of P. Okay? So let's look at our example. For example, let's label part of this tree. So I have to label the edges. This one is already called E. So let's call this A, B, C, D, E, F, G. So these are supposed to be all colors of P. And then here, I have to label this by an operation P, and this one by an operation Q. And P has to sit in P, this is a capital P, of A, B, C, E. And Q has to sit in P of E, D, F, output G. And so on. You look at the set of all possible labeling. And this becomes a contravariant functor, because if you have a labeling on this tree, you can get a labeling on this tree by assigning this vertex the composition of Q with P. You can insert the operation of P inside Q. So the action on the arrows, of type, what did I say? 2 is exactly substitution in the opera. Substitution in the opera. So just like for the nerve of simplicial sets, this disappears from the board. This nerve, here it is. For operads to dendroidal sets is going to be fully faithful. The nerve of P remembers all the structure of P. I don't throw away anything. Okay. I want to tell my categories and simplicial sets, the nerve, my operads, the dendroidal set, and I have the nerve again. And here, so here is the functor from delta to omega, and this inclusion we can call I, and it induces a can extension by shriek. It's left can extension along I. And here is the inclusion that I didn't give a name. Now, you may like to think about dendroidal sets as a topos, just like you think about simplicial sets as a topos. Simplicial sets is a very important topos. It's a classifying topos for the notion of linear order. And you may ask, for which notion is dendroidal sets a classifying topos? So I don't know the answer to that question. It's something like a multi-linear order, but I think it might also be the wrong question, because dendroidal set, you see, as a topos is also a Cartesian closed category. Yeah? So simplicial sets has a product and it has an exponential. Well, an exponential. So it has x cross y and it has y to the x. CCC. Cartesian closed category. Now, dendroidal sets also has a structure, but it has a much more important structure related to the structure of operads, which is given by a symmetric monoidal structure. So this is a symmetric monoidal should drop from perhaps, closed symmetric monoidal category given not the Cartesian structure. And the structure so I will denote it by a tensor at the whole. And it has a couple of important properties, namely, I shrink a strong monoidal. It preserves the structure. I shrink since the product to the tensor product. Okay? And also these functors have left the joints. Any simplicial set generates a category, and any dendroidal set generates an operad, and tau of x tensor y is tau of x tensor tau of y, well, this is a very classical tensor product of operads. And it's called the Boardman and Vogt tensor product of operads. Okay. So, right. So I'm running out of time, but one of the things that I'm trying to do at present with many other people is try to develop the theory of dendroidal sets analogously to the theory of simplicial sets. So there is a very nice notion of Kent complex here, and also of inner Kent complex. These give the definition of infinity operad. So an infinity operad is a dendroidal set with an extension property, just like for simplicial sets. And you can take, the main slogan is that instead of just algebras for an operad in the symmetric monoidal category, you can take algebras for an operad in a dendroidal set. And this gives again a dendroidal set. So if, and I will just do it for this operad ASS. So if X is an infinity operad, so is 1 AS X. And this is not quite consistent with the notation. Sorry. So this should be removed. Okay? And this is the dendroidal set. So remember, A sub S is the colored operad whose algebras are categories with S as objects. Now, this dendroidal set is a dendroidal set of categories with S as objects enriched in X. Yeah? So this is categories enriched in X with S as objects. And so this is a weak notion of category. The fact that this is an infinity operad means precisely that there is some notion of composition still there. Compositions exist, and they're again unique up to some homotopy. They're not given. And what you get is something which has again all the structure. It has, you can compose along a tree. You get again an infinity operad. So by iterating this, you arrive at the notion of weak high infinity. So I think I ought to stop. I started 10 minutes late, so I'm stopping in time. But anyway, this definition can be elaborated, and one can try to compare it to other definitions. And there are lots of open questions about this notion, but also already some very nice theorems coming out. So thank you very much.
By looking at internal common ones, is there, do you think, a single way to go up in the time?
Say it again?
If you got a Cartesian, monoidal structure, you can get a Cartesian structure out of it by looking at the internal coordinates. Like this thing Boardman and Vogt did in the.
You mean whether there's
Whether there's a
a
way up, whether there's a way up.
You mean whether there's a structure already on the category omega?
Yeah.
So, maybe I don't really understand your question, but the monoidal structure, let's look at this case of simplicial sets first. So there is a product on simplicial sets, and it's completely determined by what it does on the representables. But the product of two simplices is not a simplex. It's a union of simplices. And the union is exactly coded by the shuffles. So if you take a 2 simplex times a 1 simplex, you get a picture like this, and it's a union of tetrahedra. Okay, so you can go up like this, for example. It's a union of 3 tetrahedra. So exactly the same is true for omega. You can take 2 trees, and you can look at all the shuffles of the trees, but shuffling trees is a complicated combinatorial notion, and that's one way to define this. That's the product. But there isn't a monoid or a comonoid inside omega.
In the last thing you wrote down, did you put the x and the n really the other way around?
Sorry?
Are the x and the n AOS really in that order?
Yes. Yeah, so maybe to clarify this point, so if E is a symmetric monoidal category, you can view it as a colored operad or as a dendroidal set. It also has a nerve. For any tree, you can label, so the nerve of E at T is labelers of T. And you do it as follows, let me just draw a local picture. So here you put objects of E, let's call it A, B, C. Here this D, and this one you label by what I called earlier P, and P is now an arrow from A tends to B, tends to C to D. Okay? And then if you take home of nerve of P, nerve of E, that's a dendroidal set, and you calculate its value at this tree, it has one edge and no vertices, right, you get exactly P algebras in E. So it's the usual notion. The usual notion of P algebras in E. But the point is you can put other things here than nerves of symmetric monoidal categories.
Any further questions?